In this video, let's look at implicit differentiation, which is a great technique for taking the derivatives along curves that aren't functions. And the one I'd like to work with today is a circle of radius 5 centered at the origin. And you'll recall from your algebra days that the equation of this circle is x squared plus y squared equals 25. And I'd like to focus today on 3 points on this circle. The first point is at the top of the circle, and that's the point 0, 5. And you might notice there that the slope at the top of the circle we would expect to be 0. And when we do our work algebraically, we're hoping we're going to confirm the slope at 0, 5 is 0. The next point I want to focus on is the point over here on the right side of the circle, the point 5, 0. And you're already probably anticipating that we would expect to see at that location a slope that's undefined, because on the right side of the circle we have a perpendicular tangent line, or a vertical tangent line. The third point I want to look at is the point right here, the point 4, 3. And if we were to draw a tangent line at that location, we would expect a negative slope, and you might surmise that the slope perhaps would be more negative than -1. Okay, the other observation I want you to make is that unlike functions, slopes on this circle might depend on more than just the x value, and here's why. For every x value, say x equals 4, there are actually 2 y values, up here at 3 and down here at -3. And the slope up here is negative, but the slope down here will be positive. So it looks like the slopes on this circle behave not just on x, but they also behave according to the y value. And we'll see how that plays out. Alright, let's proceed algebraically now. I'll move the graph up. I'm going to go ahead and rewrite the equation of the circle. And I'm going to take its derivative implicitly. And unlike functions that we've worked with up to now, when we've taken derivatives, this equation has x's and y's on the same side of the equation. In the past, you've worked with y on one side and terms involving x on the other. Here they're mixed up. The other wrinkle is that y is now to the second power, and we haven't seen that before. So we're going to take the derivative of this equation, and derivatives involving x will feel natural, but derivatives involving y, we're going to have to apply the chain rule. And y squared, its derivative will involve bringing the 2 down and getting y to the first, but then we're going to remember that y ultimately depends on x. So when we differentiate, this is the interior function, and we'll have to attach a dy dx. Let's see how that plays out. Alright, so the derivative of our first term right here, as you'd expect, is 2x. The derivative of our second term is going to be 2y, as you'd expect, but because of the chain rule, we have to multiply by dy dx, and that's the derivative of this interior function. Okay, now the derivative on the right-hand side of 25 is just 0. So there's an equation that involves our slopes, dy dx. And ultimately what we're trying to do is isolate dy dx. We want to know how the slopes on the circle behave, and that expression is modeling those slopes. So we're going to take the 2x, put it on the right, we're going to divide by 2y, and then dy dx will be all by itself. So when you do those two steps, you get dy dx equals -2x over 2y, which simplifies to -xy. And just like we anticipated, the slopes on the circle depend not only on the x-coordinate, but also on the y-coordinate. This is the first time we've seen that. Alright, let's take our dy dx expression now, and let's see if we can evaluate it at the 3 points along the curve that we identified earlier. So first we're going to identify dy dx at 0, 5. Then we'll evaluate dy dx at 5, 0. That's on the right-hand side of the curve. And then dy dx we'll evaluate at 4, 3. And in each case, we're going to take the x and the y coordinate and plug them into negative x over y. Here goes. First we get negative 0 over 5, which is 0. So at the top of the circle, the slope is 0. Terrific, that's exactly what we anticipated. Let's do the second one. dy dx at 5, 0 is going to be negative 5 over 0. And you know that's undefined, and that's terrific. That's exactly what we anticipated. At the top of the circle, sorry, on the right-hand side of the circle, the slope is undefined. And then finally at dy dx at 4, 3 is negative 4 thirds. And that's a negative slope, slightly more negative than negative 1, precisely what we anticipated earlier. And I'll just go back to that picture so that you can see that. So here's the circle. The slope at 0, 5 is 0. The slope at 5, 0 is undefined. And the slope at 4, 3 is negative 4 thirds. I'll leave it to you to figure out the slope at 4, negative 3. And I'm hoping it will be consistent with the slope of that tangent line. Alright, back to the bottom of the page. Let's conclude now by looking at an example of a more complicated implicit differentiation problem. And I'm going to just change the color of the pen, just for variety's sake. And I'm going to invent a curve, and we're going to differentiate it implicitly. And here's the curve. X cubed plus x to the 8th y to the 5th minus 9y squared equals x. I have absolutely no idea what that curve looks like, and you probably don't either. But we don't even need to see a picture of it to explore how its slopes are behaving. What we're going to do is walk across this equation and take the derivative implicitly. And by implicitly, we simply mean that when we get to a y and we're differentiating it, we're going to attach dy dx. Same thing will happen over here. So here goes. The derivative of x cubed is 3x squared. The derivative of x to the 8th times y to the 5th is a product, so we're going to have to use the product rule. X to the 8th is going to be our u, y to the 5th is going to be our v. So here's the product rule. U prime v plus u v prime. And I'm hoping that you anticipated that I'd be throwing a dy dx in there, because y has a derivative. Alright, let's continue now to the next term. The derivative of 9y squared is 18y to the 1st times the derivative of y. And on the right-hand side of the equal sign, the derivative of x is 1. Now that looks like a big mess, but all we have to do at this point now is take these terms that don't involve dy dx, and we're going to send them to the other side of the equation. We'll factor out dy dx from the remaining terms, and then we should be able to clean things up. So here goes. The two terms that remain on the left-hand side are the ones that involve dy dx, and I'm factoring them out, and I'll get 5x to the 8th, y to the 4th, minus 18y. And on the other side of the equation, we're going to have 1 minus 3x squared minus 8x to the 7th, y to the 5th. The only thing left to do now is to solve for dy dx. So, dy dx equals, and our numerator will be all the terms on the left, or sorry, on the right, and our denominator will be those terms that are in parentheses. And there you have it. That's how you get the slopes along that messy curve that I had written down just a moment ago.